Okay, in today's lesson we're looking at 14e, symmetry properties of circular functions. Our learning intention to explore the symmetry properties that they have, and to know whether we've met the learning intention, can we interpret the symmetry properties of the circular function sine, cosine and tan. So to kick things off, we're going to introduce the idea of the quadrant system. So starting at 0 degrees, from the x-axis to the y-axis, through 90 degrees or pi on 2, we have quadrant number 1. From 90 degrees to 100 degrees, or from pi on 2 to pi, we've got quadrant number 2. Likewise, quadrants 3 and 4. And we're going to look at the properties that each of the circular functions have in each of the 4 quadrants. Now these 4 quadrants can be used for angles greater than 360, because as the angle increases past 360, then we just return back to the first quadrant. As we go through 4 pi, through 720 degrees, then we return back to the first quadrant. So we really only need to generate ideas and properties for the 4 quadrants only. Okay, so let's look at the properties of the first quadrant, where theta is between 0 or pi on 2. The angle that we can use is we can just take theta, and we'll look at alternatives to that in just a moment. So, in quadrant 1, the x and y coordinates are positive. We've got a positive value for our x coordinate, and we have a positive value for our y coordinate. So, because of this, we can say that the cos value will always be positive in quadrant 1. The y coordinate, the value of sine of theta, will also always be positive in quadrant 1. And therefore, if we take a positive and always divide by a positive, then tan will also be positive in quadrant 1. So, in quadrant 1 here, all of the circular functions are positive. Let's take a look at quadrant number 2. Okay, in the second quadrant here, from theta is between pi on 2 and pi, we can use the angle theta, take away pi. That should say pi, take away theta. So and how we can generate this is we take pi and then subtract theta, so move in a clockwise direction around to obtain our angle here. So let's look at the coordinates for a moment. The x coordinates in the second quadrant are always going to be negative. So our cos values will always be negative. We're still above the x-axis for all of the y values, which means that sine will always be positive. But when we look at tan, if we take the y values, which are always positive, and divide them by our x values, which are always negative, our value for tan in the second quadrant of an angle that falls within the second quadrant will always be a negative number. So in the second quadrant here, only sine is always positive. There we go, that's the correct way around this time. The third quadrant. Okay, so let me just put that up a bit. In the third quadrant, where angles are greater than pi but less than 3 pi on 2, so we're dealing with these lot of angles around here. And we could also say that the angle is from pi plus theta. Both the x and y coordinates in this quadrant here are negative. Therefore, only the tan function is going to yield us positive results. Always have an x coordinate which is negative, always have a y coordinate which is negative, but when we take a negative over a negative, that is going to yield a positive result. So that just leaves us with the fourth quadrant. Okay. The fourth quadrant, or the quadrant here, is referring to angles greater than 3 pi on 2 but less than 2 pi. And as we can see, if we're always dealing with values of x which are on the right hand side of the y-axis, then the x-coordinate will always be positive. The y-coordinate will always be negative, which means taking a negative y-coordinate, dividing by a positive x-coordinate will always yield a negative tan, which means that the fourth quadrant will always yield a positive cos value. Now, for those of you who are locals, a useful acronym we could use is all stations to Caulfield. All stations to Caulfield. Starting from 1, 2, 3, 4, all stations to Caulfield. Okay, so negative angles. If we have negative angles, then what that's saying is the angle traverses in the opposite direction or in a clockwise motion, starting from here. So it would traverse through the fourth quadrant first. Now, as we can see, that having a negative theta is going to give us the same x value, okay, comes to the same x value as here, but the y coordinate is a negative value of the same y coordinate. So we're going to explore this in some worked examples just below. Okay. Worked example number 1. If sine of x is 0.6, find sine of pi minus x, sine of pi plus x, and sine of 2 pi minus x. So what that's saying is we have sine of a particular angle, and the value is 0.6. So sine of a particular angle is giving us 0.6. So the y-coordinate roughly up here somewhere. So if we had that same angle and subtracted that from pi, what value would that give us? So let's just explore this on a unit circle just for a moment. Oops. All right, if there's a unit circle here, and we have some angle of x, which goes a little bit over halfway up the unit circle, to a y-coordinate of 0.6 for some angle x. Then, if we are taking pi minus x, which quadrant is that in?
Kathleen McLeish, please come to the front office for a message.
So this is actually referring to an angle in the second, or if we take pi is here, and then we subtract the angle, so we're moving in a clockwise direction. Then that gives us the same angle here, but in the second quadrant. So this is giving us a value in the second quadrant. So in the second quadrant here, the same angle goes up. What is the corresponding y value here? Well, it's going to be the exact same. So sine of pi minus x is equal to sine of x, so it's equal to the same value that we had before, and the value that we had before was 0.6, so this could be said to be the same as 0.6. Alright, let's have a go at the second one. What quadrant is this in? Well, angle pi is around here, so pi plus whatever the angle x is must fall in this region here. So in the third quadrant, we know that sine is a negative value. So if we're taking away that x value, if we're subtracting that x value, then the y value is going to be the same magnitude, but the negative value of that magnitude. So sine pi, pi plus x is equal to negative sine of pi, of x equals negative 0.6. And lastly, for sine 2 pi minus x, 2 pi is a full revolution, and then we're subtracting the angle down here, which means we're in the fourth quadrant. And in the fourth quadrant, sine is negative again. Now if we wanted to draw it again, we could subtract this same angle. Down here, same magnitude, but the negative of that magnitude. Okay. All right, let's look at the second example here. Find x if sine x equals negative sine pi over 3, and where the angle x is between pi and 3 pi on 2. So, first of all, let's determine what quadrant we're in. The angle is greater than pi, so we are in the third quadrant. Why do we do that? Once we've identified which quadrant we're in, we can come up with a alternative version of this if it is in fact in if it is negative in those quadrants. So what we can say therefore is that this sine x can be written as sine of pi plus theta, where theta is the angle. But we also know that in the third quadrant, we're going to have the negative value of what it was in the first quadrant. So, we have also been given a value that we can use here and here. So let's substitute in theta for pi on 3. Okay. Which means that we must have an angle x of pi plus pi on 3 for pi over 3. So, if this is our positive value of sine, then x must be 4 pi over 3. In the second example, we're being asked to find x if cos of x equals negative cos of 30 degrees, where the angle is between 90 and 180. So in this angle range, we're looking in the second quadrant. And what do we know about the second quadrant? We know that cos is negative, but we can also write the angle as pi take away theta. So we can use both of those facts, cos pi minus theta is equal to negative cos of theta. Now, the angle that we were given was 30 degrees, so we could say, actually, let's not write pi, let's write 180, because we're using degrees and not radians. Okay, so let's put in our 30 degrees. So cos of 180 minus 30 is equal to negative cos of 30 degrees, which means that cos of 150 equals negative cos of 30. Therefore, the angle x must be 150 degrees. So, what essentially have we done here? Let's just look in terms of that second example. Cos of 30 degrees. So if we have 30 degrees here, everyone can kind of imagine what 30 degrees look like. That's probably closer to 45, but just to really exaggerate the fact, let's say that that's 30 degrees. Now, the x-coordinate of 30 degrees is whatever. We've got an x-coordinate here, so let's say x-coordinate. Now, if we're told that to take the negative of this x-coordinate, then that in fact is all the way over here. A negative x-coordinate. So what we've essentially done is we've used the symmetry properties that in the second quadrant we could take away 30 from 180, and then we can make these two circular functions equivalent to each other. We can use the negative of sine 30 and the sine 50 function, which we didn't know was sine 50, to discover what our original angle x must have been. And without using any graphs just yet, that is a quick introduction into our symmetry properties of circular functions.